So hyperbolas are, what's this, our third conic section here. And note that our equations for an ellipse, say x squared over 16 plus y squared over 25 equals 1, just dealt with that. If we make just one little change, and you can say, oh, it's just a little change, it's just a change of sign from the plus to the minus, our graph goes from our transformed circle, our vertically stretched circle, in this case, to something that doesn't look at anything at all circle-like, again with just that one change of sign. The shape is called hyperbola. Each side of hyperbola is called a branch of the hyperbola. Hyperbola has two branches in this case. We'll note that both our ellipse and our hyperbola have certain symmetries. Since I can replace x with negative x and nothing changes, I replace y with negative y and nothing changes. We note that both the ellipse and hyperbola are functions that have symmetry with respect to both the y-axis and the x-axis. So arguably, if you can get part of a branch of a hyperbola done, hyperbola centered at 0, 0, by symmetry, then you can certainly get the other parts of your hyperbola done. Ditto with an ellipse. If you get one quadrant done, you know you have symmetry with respect to the y-axis. You then know you have symmetry with respect to the x-axis. So you can, again, through symmetry, by graphing just a small piece of your ellipse or hyperbola, generate the other parts of it. So let's consider a hyperbola. Just want to look at viewing it a little differently. Our standard form is either an x squared or y squared over a number minus the other, x squared or y squared over a number, equal 1. Let's suppose we go and think about rewriting and solving this particular hyperbola's equation for y. First step is I move the y squared over 25 over to the right side, move the 1 over, rewrite, I get to here. Then go ahead and multiply both sides by 25, which takes me to here. So next, let's go ahead and take the square root of each side. I take a square root, I get plus or minus 5. Square root of x squared over 16 minus 1. And my question now is, what happens as x gets very, very large or very, very small? Say 1,000, 100,000, a million. Basically, this 1 doesn't have too much of an influence here on this expression right here as x gets larger and larger or x gets smaller and smaller, again heading toward negative 100, negative 1,000, negative a million. So basically, for large numbers, we could say the limit as x heads to 1,000 toward infinity or x heads down to negative infinity, this y is going to be approximately plus or minus 5 times roughly x squared over 16, because that 1 really isn't going to have much of an influence, or plus or minus 5 times, well, the square root of x squared would be x. I've already got the plus or minus taken care of. The square root of 16 is 4, or pretty much now plus or minus 5/4. As x gets very, very large, that is, or very, very small, we have our y values, our outputs, heading to plus or minus 5/4. And I'd like to notice what we see up here in our original equation. I see a 25 is 5 squared and a 16 is 4 squared, and I see this plus or minus 5/4. This is a specific case where we can generalize this and then use this information to help us get a graph of a hyperbola done quickly and easily. So we've got our hyperbola here, and we just looked at in the last slide and noted that as x got larger and larger, or x got smaller or smaller, our outputs, our y's, approached plus or minus 5/4 x. And note we see a 5 is the square root of 25, and a 4 is the square root of 16. And we consider these values that our y's approach, the plus or minus, the two lines, plus 5/4 x or negative 5/4 x. We call those asymptotes, and we will draw them in to help us see where our hyperbola goes as dotted lines. And we know from previous work with hyperbolas, the hyperbolas either open up and down, two branches opening up and down, or two branches opening left and right. Looking at our original equation here, x squared over 16 minus y squared over 25 equals 1, note x equals plus or minus 4 is a quick visual solution here. 4 squared or negative 4 squared over 16 is 1. So 4, 0 and negative 4, 0 are going to be points here on the graph. Here's my 4, 0. Here's my negative 4, 0. And so clearly, if those points are there, then I'm going to know that this is a hyperbola which opens left and right. Now, we've said as x gets larger and larger, I'm going to approach either that 5/4 x, or I'm going to approach that negative 5/4 x. Or as x gets smaller and smaller, I'm going to approach that negative 5/4 x, or I'm going to approach that 5/4 x, and you can then see how your hyperbola, the branches are going to appear. And clearly, the larger x gets, the closer and closer that vertical distance is going to be between my hyperbola and its asymptote. That vertical distance diminishes the bigger x gets, or the smaller x gets. So a method you probably learned last year for graphing hyperbolas, which kind of, again, makes into an algorithmic process what we just discussed in the previous few slides, is to go ahead and draw what's called your representative rectangle to locate your vertices and your asymptotes. So clearly, looking at this setup, 4, 0 and negative 4, 0 are going to be 2 points that satisfy the equation of the hyperbola. And then the key was to say, well, let's look at and go ahead, even though obviously this term can never equal 1, what would create this fraction to be 1? And the answer was if I have a 5 or a negative 5. So then letting the 5 and negative 5 and the 4 and the negative 4 be midpoints of the sides of this rectangle here, I then drew in the diagonals of that rectangle, which go through the origin, and I then, those diagonals when extended are the asymptotes for my hyperbola, and I then can sketch in that the two branches for my hyperbola. And again, as x increases or decreases without bound, my the branches of my hyperbola come closer and closer to those asymptotes. So the geometric definition for hyperbola, similar to for an ellipse, just a little bit different, one change in operations. If you have your two fixed points, which you can call your foci, F1 and F2, I'm looking for all points in the coordinate plane, x, y, such that not that the sum of these two distances is a constant, but such that the absolute value of the difference, is some constant, let's say 2a. So again, if I want the absolute value of the difference, depending on whether d1 is bigger than d2, if I go d2 minus d1, well, that's going to be a negative number. And I'm interested again in the absolute value of that difference being a constant. So I could also write that as, for example, d1 minus d2 equals plus or minus 2a. That would be equivalent. And the book waves its hands at this a bit, as will we. If you go ahead and simplify, if you go back in a coordinate system and you go ahead and set this up using the distance formula, and simplify, eventually you're going to get to a point where you're going to get, say, in this case we're looking at, say, a horizontal, hyperbola that's going to open left and right. Eventually you're going to get down to an x squared over a number minus a y squared over a number equals 1. Now, tied in with that derivation, we also want to talk about the relationship among, for example, say this is a 4, that's a 25. What's the relationship between the 4 and the 25 and the coordinates of our foci? And again, this is going to be, in this case, a hyperbola that opens left and right, because clearly 2, 0 and negative 2, 0 are going to satisfy the equation. And so the question is, where do our focal points go? And the answer is the focal points go inside. It's going to wind up, they're going to be inside of the bowls formed by the branches of the hyperbola. And the relationship here is the following. If we're going to call this, say, C0, and the focal point over here, negative C0, it turns out that, and again, it should make a little bit of sense, note that this x-coordinate is bigger than here. And so it should make sense that our Pythagorean relationship here looks Pythagorean, is c squared equals the a squared plus the b squared given in your equation, general equation for the hyperbola. So in this case, our c squared is going to be 29. Our c is going to be root 29. Note, then you're going to have root 29 is clearly bigger than 2. So it's going to lie well to the right of 2. Root 29 is about somewhere between 5 and 6. So it's going to be over there a fair amount. So suppose I were asked to come up with vertices, equations of asymptotes, sketch a graph of this hyperbola that looks fairly nasty and complicated because I don't just have an x squared or a y squared. I want to approach that the same way we've approached graphs for the last several weeks. If I replace x with an x minus 3, I'm going to translate everything 3 units to the right. If I replace y with y plus 7, everything goes down 7 units. So to answer this question, to graph this and talk about where the coordinates of the foci are, what the equations of the asymptotes are, etc., I'm simply going to look at my more general hyperbola centered at 0, 0 and simply translate everything 3 units right and 7 units down. So if I look at this hyperbola over here, I know that my vertices here are going to be plus or minus 2, and I know I'm going to open left and right. And if I draw my representative rectangle in here, and I don't need to draw actually the whole thing in, I could draw just the top half and that'll get the job done. I'm coming up here at 10, so I've got a 10 here. I'm coming over here 2, so if I look at that equation for my asymptote here, the slope's going to be 10 over 2 is 5, so that's going to be a 5x. So the equations for my asymptotes here are y equals plus or minus 5x. Again, I've got 2, 0 and negative 2, 0 being two of my vertices here for the hyperbola. So now go ahead and talk about where's this thing going to go. Well, the center is going to move from 0, 0 on this one. The center is going to move 0, 0 over to 3, negative 7. Right 3, down 7. So if I want to know where my two vertices are, the 2, 0 is going to move to, let's see, that would be 3 units right and 7 units down. That's going to go down to 5, neg 7. And the negative 2, 0, if I move 3 units right and 2 units down, I'm going to go, or 7 units down, I'm going to go 1, negative 7. How about the equations of my asymptotes? Well, my asymptotes were plus or minus 5x. Move 3 units to the right. That's going to replace x with x minus 3. And 7 units down, it's going to replace the y with y plus 7. And I can leave my equations for the asymptotes in that form, or if I want to, if I were asked, I certainly could put them in y equals mx plus b form by multiplying out. Just to do one of them, y plus 7 equals, say, negative 5 of x minus 3, y plus 7 equals negative 5x plus 15. Go ahead and simplify that. Y equals, move the 7 over, 15 minus 7 is 8, negative 5x plus 8. That would be the equation of one of my two asymptotes.